Let's talk about an overview of differential equations. So what is a differential equation? A differential equation is an equation that contains an unknown function and some of its derivatives. Now, its derivatives could be partial derivatives or ordinary derivatives, as we have been discussing. We do not talk about partial derivatives in this course, but in future courses, you'll discuss partial derivatives. So, here are some examples of differential equations, ones we've worked with: y prime equals dy dx, or something of this form, like a times y double prime plus b times y prime plus c times y, the original function, equals 0, or x times y prime plus y equals y squared, or in different variables, dp dt, like say p is a population, dp dt is equal to 1.2 times p times the quantity 1 minus p over 4,200. So these are all examples of differential equations, some of which, the first and the last, are similar to things that we have looked at in our previous sections in Calc 1 or Calc 2. What we define as the order of a differential equation is the largest derivative that is present in the equation. So this is a first order. This one right here is a first order differential equation, whereas this guy would be a second order because there's a second derivative in this second equation. Now, what is a solution to a differential equation? The solutions to differential equations are functions. The function or the general function, the specific or general function that would satisfy the differential equation. So the solution to the first one would be the function y. Y is a function of x that satisfies y prime equals dy dx. The solution to the second differential equation example we have above would be the function y that satisfies this equation when we take the second derivative of the function and multiply by some constant a plus b times the first derivative of the function plus c times the original function. All of that would add together and give us 0. That would be the solution. Whatever function or general function satisfies, general family of functions satisfies that differential equation. So a solution to a differential equation is the function y equals f of x if we're talking in terms of x and y as our variables, if the differential equation is satisfied when we plug that function and its derivatives into the differential equation. That's what makes a solution. So those are just some of the language that we're going to be working with: the order of a differential equation, the solutions to differential equations, and we are going to actually start by verifying functions are solutions to specific differential equations. So let's look at a couple examples. So let's take a look at this first example. Let's verify that this function, y of x, we're talking about functions of x in this case, y of x equals 1/2 x cosine of x. So let's take this function and let's verify that this is a general solution to the differential equation y double prime, so it's a second order differential equation, plus y equals the sine of x. So how am I going to verify that? Well, I need to find the second derivative, and then I'm going to take my function, plug it in for y, plug the second derivative in for y prime, and see if that is, in fact, if I'm trying to verify, see that that is in fact going to equal the sine of x. So that's what I'm going to do. And so let's jump right into it. I'm going to get rid of some of my highlighting on that differential equation. So we start with y. Y is, good practice with our derivatives, y is minus 1/2 x. Now this has a times cosine of x. So we're going to have to apply the product rule. So work with our higher order derivatives here and take the product rule. So when we take the first derivative here, to get to the second derivative, obviously we need the first derivative. Even though it's not in the differential equation, we still are going to need it to get to that second derivative. So y prime, we have to apply the product rule. So we take the derivative of the first, we get minus 1/2 times the cosine of x. Then we have to take the derivative of the cosine, which is minus sine of x times minus 1/2 x. And let's just simplify that before I find the second derivative. So we get minus 1/2 cosine of x plus 1/2 x sine of x. And now let's find the second derivative. And I'm just going to keep working my way down. So that was the first derivative. Now let's find the second derivative. Now to find the second derivative, I am going to have to once again apply product rule to my second term here because it is a product. But I don't need to I did do product rule up here, but I don't need to do product rule in the first because that's just minus 1/2 cosine. So the second derivative, when I take the derivative of the cosine, I get negative sign, so that becomes positive 1/2 sine of x. And then I got to do the product rule over here, so it's going to become 1/2 sine of x. And then the derivative of the sine of x is cosine of x times 1/2 x. And then we'll just simplify that as well. Kind of conveniently here, 1/2 sine of x plus 1/2 sine of x gives me just sine of x. And then we've got 1/2 x cosine of x. Get those, combine those terms. So now I have my second derivative. So I have my function, my first derivative, and I have my second derivative. Now we want to verify the solution. So we're trying to verify that y double prime plus y is in fact equal to the sine of x. So let's go ahead and plug in y double prime. Y double prime was sine of x plus 1/2 x cosine of x. And y, let's keep y there. Y was minus, plugging in y, minus 1/2 x cosine of x. And we want to know, does that in fact, that's what we're trying to verify, equal the sine of x? Well, look at that. It does, because we have plus, we're just adding those two. The only reason I put those in parentheses was to show that this was y double prime and this was y. But look at that. Those two would cancel out, and we end up with the sine of x does in fact equal the sine of x, and we have verified the solution by showing that the second derivative plus the original function that we were given was equal to the sine of x. Okay, so let's take a look at another example. Let's verify that this function, y of x equals c1 e to the negative x plus c2 e to the positive x, is a solution to this given differential equation, y double prime of x. Now in this case, I'm just using different notation to get us comfortable with it. So y double prime of x, so we're talking about a function of x, its second derivative, this function up above, minus the original function, y of x, is going to be equal to 0. And in this case, we do just have those two constants running around. So when we're taking the derivatives, we're just going to do this for those generic constants, those arbitrary constants. So we're going to do the same thing we did on the last example. We're going to start with y of x, which was c1 e to the negative x plus c2 e to the x. And to get the second derivative, we have to start with the first derivative. So we're going to take the first derivative. The first derivative, we do have to use a little chain rule on that e to the minus x. So that, although that constant is just a constant. So when we take the derivative, the constant multiple continues to just stay there. We get c1 e to the negative x, but then we have to multiply by a -1. Plus we get c2, and the derivative of e to the x is just e to the x. So the first derivative is minus c1 e to the negative x plus c2 e to the x. And then we need the second derivative if we're going to be checking that differential equation, because it had the second derivative in it. So the second derivative of e to the x is going to be minus c1 e to the negative x times the -1 plus c2 e to the x. So the second derivative is a c1 e to the negative x plus c2 e to the x. And we need to check that the second derivative of x minus the original function y of x is equal to 0. The second derivative of y with respect to x minus the function of x is equal to 0. Okay, so we're going to plug those in. So we're going to plug in the second derivative, c1 e to the minus x plus c2 e to the x, and we're going to subtract the original function. Now, I should have mentioned over here, and we can see it right here. Notice what happened because of the nature of the derivatives of the exponentials and that cycling with the chain rule of that negative sign between positive and negative values. The second derivative and the original function are actually the same. They are equivalent. So of course, when we subtract them, and you can see that here, we've got a positive c1 e to the negative x. And then we're going to end up with a minus. So we've got c1 e to the minus x plus c2 e to the x minus c1 e to the negative x minus c2. I got going and talking and didn't carry my subnotation there. c2 e to the x equals 0. And you can see those are going to cancel and those are going to cancel. And 0 does in fact equal 0. So we have verified that it is a solution. So we have verified it's a solution by checking, by taking the derivatives and plugging them in We only needed the second derivative by plugging the second derivative in the function into the differential equation. We were able to verify that this is, in fact, a solution to that differential equation.